Okay, so today we're going to learn about a fun little topic called the logistic growth model. And this is one particular solution to a particular differential equation that sometimes gets focused on the AP exam and is really pretty interesting. I will say usually I do a really cool simulation activity to teach this, and it's just not going to work without me being there, and I apologize for that. But we're going to try and get the point across anyway, okay? So we're going to consider the spread of a rumor amidst a population of 40 people. And each day, everyone who has heard the rumor can tell one person, and they choose that one person at random. And what we would be doing if I were in class is doing a simulation to see how fast this rumor spreads. And so what I did is I saved the data from last year, and we're just going to use that data. So what I would have done is assign each of you a number, and some of you were going to have to represent more than one person because I needed a sample size of 40. With a smaller sample size, there's too much kind of random variation and it doesn't really work out. And so each of you would be one person, or some of you would be two people with like a split personality or something. And on the first day, I'm the only person that knows the rumor. There's only one person. And then what I would have done is use the random number generator in the calculator and choose one person that I would tell the rumor to. Okay, so I choose one of you, and now at the end of day 2, there are 2 of us who know the rumor. But that means that there are 2 of us who can tell the rumor to somebody else. So then I would use the random number generator, and I would pick 2 numbers. One for the person that I'm telling, and one for the person that the person I already told is telling. So by the end of that day, there are now 4 people who know this rumor. Next day, I choose 4 random numbers, and now there are 8 people who know this rumor. Okay? So that day, I choose 8 random numbers. Now, how come this didn't go from 8 to 16? How come these numbers don't keep doubling every time? Well, the reason for that is by the time there are 8 people, when I choose 8 random numbers, there's a good chance that I choose somebody who already knows the rumor. Okay, so when I tell that person, they're like, wow, thanks, Miss Kramer, but I already knew that. And that starts to happen more and more as we approach the size of our entire population, which in this case is 40. You know, at the end of day 9, there are 38 people who know the rumor and tell somebody else, but most of the people they tell already know it, okay? So that growth starts off exponentially, but then it starts to level off, okay? Those of you who are in or have already taken AP statistics, I want you to get out a graphing calculator and make a scatter plot of this data. So I want the explanatory variable to be the day and the response variable to be the number of people. And I want you to share this with your classmates who are not in stats so that they can see what this relationship looks like. Pause the video and do that, but quickly. Okay, I have done that because I'm cool. And I've got the day in list 1. I've got the number of people in list 2. And I'm going to make a scatter plot. And this is what it looks like, which is about what I expect. It looks like exponential growth that then levels off. Okay, so probably in the beginning, you were talking about a rumor spreading. You were thinking about exponential growth. But we have a limit to what this can approach. This cannot go above 40. More than 40 people cannot know this rumor because there are only 40 people available. Okay? So before we talk about that kind of model, I do want to talk first about exponential growth. Exponential growth means that the growth rate is proportional to the size of the population. In other words, dp/dt, the growth rate of the size of the population, is proportional to the size of the population. K is just the constant of proportionality. So I have dp dt is equal to K times P. This is a differential equation that I can solve. dP over P is equal to K times dt. And I can integrate both sides. I get the natural log of the absolute value of P is equal to K times T, which if I e to the both sides, I end up with P is equal to, I'm sorry, this should have had a plus C, C e to the KT, and that is an exponential model, okay? P is the size of the population as a function of time, and it's equal to some constant, which is usually the initial condition, times e to the KT, where K is just that constant proportionality. However, in real life, populations cannot grow exponentially. There are limiting factors. So if you think, let's think biology. We've got like a group of deer on an island or something like that. What kinds of factors limit the growth of that deer population? I want you to shout some out right now. Okay, I'm hoping you are thinking about things like space, the amount of food, the number of predators, sorry, but waste. Okay, when we hit a certain point and the waste starts piling up, I don't know, animals don't survive so well, yeah. Water, okay, things like that. And I'm sure you thought of some more brilliant things. But these are the ideas, is that there are factors that limit the growth of a population. Space is usually a big one, okay? When we run out of room, we kind of just can't do much, okay? So a much more realistic model, one that takes the carrying capacity of an environment into account, is called the logistic model, which is the one that we're going to learn about today. Okay, so logistic model takes into account the fact that a population cannot just grow unbounded. In logistic model, the population growth rate is proportional to both the population size. Okay, the larger the population is, the more individuals there are for breeding, which means the population is going to grow. But it also takes into account how far away we are from the carrying capacity. Okay, and we're going to call the carrying capacity M. So, dp dt, the growth rate of the population, is proportional to both the size of the population and how far I am from the carrying capacity. If I'm far from the carrying capacity, then there aren't a lot of limiting growth factors like space and water and food and things like that. But if I'm getting really close to the carrying capacity, then this is going to be a small number, which is going to mean my population is not growing very quickly because I'm getting close to my limit. All right, so like I said, that gives us dp dt is equal to K times P times M minus P. Or sometimes they factor out an M. M is a constant, right? It is the carrying capacity. And they factor out that M and lump it in with this constant. If I factor M out of here, I get 1. If I divide this by M, I get P over M. All right, so these are two different ways to write the same differential equation. We could solve this. We're not going to. I don't want to. If we did, it would give me this. The size of the population is equal to the carrying capacity over 1 plus some constant times e to the negative kt. On the AP exam, this is not nearly as important as the form of the differential equation, but we are going to spend some time focusing on this solution in class. All right, so here is a slope field to represent all the different solutions to that differential equation. Notice the slope field starts above the carrying capacity. Do we see that this guy is the carrying capacity? It's what I'm approaching. It's what I level out to. But notice a solution that starts above the carrying capacity is going to get sucked in here. If we start above the carrying capacity, if there are more deer on the island than the deer can support, what happens? Well, the deer die off until we approach this carrying capacity. Do we see that? Okay, so I'm going to ask a few kind of critical questions about this model. The first, what is the limit of the size of the population P as T approaches infinity? So as T is approaching infinity, what happens to the size of the population? Well, regardless of if I start above or below the carrying capacity, I am approaching the carrying capacity. So this is true for any logistic model. As time goes to infinity, the size of the population approaches the carrying capacity. Next question, when is the population growing the fastest? When does this have the steepest slope? It looks like it's happening in here. What would your guess be? You're probably right. It's whenever the population is at half its carrying capacity. Okay, at m over 2. Now that doesn't answer the question when. That answers the question at what population size. But that's probably what they'll ask on the AP exam. We are increasing the most rapidly at half carrying capacity. So let's do an example. A state game commissioner releases 40 elk into a refuge. After 5 years, the elk population is 104. The commissioner believes that the environment cannot support more than 4,000 elk. I want a general model for the rate of change of the elk population, and I want a model for the elk population in terms of T. So I want both the differential equation and the solution. This 40 is my initial condition, so I know that 0, 40 is part of my solution. And it says after 5 years, the elk population is 104. So 5, 104 is part of my solution as well. And I know that m is equal to 4,000. So let's start with our differential equation. I've got dp dt is equal to k. I don't know why I didn't do an equal sign. I'm sorry. Is equal to k times p times m minus p, but m is 4,000. Or I could have written this as a different constant times p times 1 minus p over 4,000. Either of those would be fine. Okay? And it just says the general model, so it's okay to keep this k here. Part B wants us to actually solve for the elk population in terms of time. Okay? So, P is going to equal m over 1 plus ce to the negative kt. But I know m is 4,000. I also have an initial population and another point later on in time. So I have 2 unknowns, c and k, but I have 2 points. So I'm going to be able to solve for both of those. I'm going to use my initial condition first, and I'm going to do 40 is equal to 4,000 over 1 plus c e to the negative k times t is 0. Okay, so this gives me 4,000 over 1 plus e to the 0 is 1. This is just c, and I can solve this for c. So I'm going to multiply both sides by 1 plus c is equal to 4,000. I'm going to divide both sides by 40, and I get c is equal to 4,000 divided by 40. And then I'm going to subtract 1, and that gives me c is equal to 99. Okay, I'm going to erase and make some space for myself up here. And so now I have P is equal to 4,000 over 1 plus C. Oops, sorry, C was 99. That's what we just found. 99 e to the negative kt. All right. Now I'm going to use my other point, and solve for k. My other point is 5, 104. So I've got 104 is equal to 4,000 over 1 plus 99 times e to the negative k times t is 5. And I'm going to solve this for k. Pause right now and do the algebra and see if you get what I get. Okay, so I'm going to multiply both sides by the denominator. I have 104 times 1 plus 99 e to the negative 5k is equal to 4,000. And I'm going to divide both sides by 104. So I have 1 plus 99 e to the negative 5k is equal to 4,000 divided by 104, which is 38.4615. Keep all these numbers to be accurate, okay? Our final answer needs to be accurate to 3 decimal places. So I'm going to subtract 1 from both sides, which is going to give me 37 point whatever. And I'm going to divide both sides by 99, which is going to give me e to the negative 5k is equal to 0.3885 something. All right. To solve, I need to take the natural log of both sides. If I take the natural log of this side and the natural log of this side, that leaves me with negative 5k is equal to the natural log of that 0.388 whatever, which gives me negative 0.94546 something, which means k is equal to 0.18909. 222. That's probably enough. So let's write my final answer. I'm going to get rid of all this stuff. And I get P of t is equal to 4,000 over 1 plus 99 e to the negative 0.189. I'm going to stop there. T. Again, this is not the kind of skill that they're going to test on the AP exam, but I have seen questions that ask you to use the P of t equation, so we do sometimes need to be able to do this, okay? It's not nearly as big of a skill as understanding the properties of logistic model, but it is important. All right. I want us to use that model to estimate the population after 15 years. I want to find the limit of that model as t goes to infinity. In other words, the limit as t goes to infinity of the size of the population. And I want to know when the population is growing the fastest. Okay, so I'll bring that model back up in case you didn't get that written down. Here it is. Okay, and I want you to answer those questions. Actually, I think I can cut this and move it over. Okay, so to estimate the population after 15 years, what are you going to do? Well, you're going to plug in 15 for t. So it's going to be 4,000 over 1 plus 99 times e to the negative 0.189 times 15 which gives me 587.101. So about 587 elk. Find the limit of the model as t goes to infinity. That should be easy. That is the carrying capacity, 4,000. And then finally, when is the population growing the fastest? Well, we know what the size of the population is when it's growing the fastest. It's 2,000 is equal to 4,000 over 1 plus 99 e to the negative 0.189t. And we can solve that for t, okay? And when I solve that for t, I get about 24.3 313 years. So the population will be growing the fastest about 24 years later. I'm not too worried about the accuracy here. I just want to make sure we're getting the concepts right now. All right, here's another example for you guys to be working with. There are 10 grizzly bears introduced to a national park 10 years ago. There are 23 bears at the present time, and the park can support a maximum of 100 bears. I want you to write the equation for P of T, and I want to know when the bear population will be growing at a maximum. Okay, so solve this, pause. Okay, when I solve, I get P is equal to the carrying capacity over 1 plus CE to the negative KT. The points that I have are times 0, 10 bears, and 10 years later, 23 bears. All right, so I can immediately plug in my carrying capacity, which is 100 over 1 plus C e to the negative KT. The first thing I'm going to do is plug in my initial condition. 10 is equal to 100 over 1 plus C e to the 0, which gives me C is equal to 9. All right. So I'm going to race up to here and plug in 9 for C. Okay, so C is 9 and M is 100. And I can use the second point, 23, as P, and 10 as T, and I can do that and solve for K. And when I do that, I get 0.09889, which gives me a growth model of 100 over 1 plus 9 e to the negative 0.09889 t. For the second question, when will the bear population be growing at a maximum? This happens at half the carrying capacity. So I'm going to take my model and set that equal to 50 and solve for t. When I do that, I get t equals 22.219 years later. So 22.219 years from the initial, which since the initial was 10 years ago, that means 12 years from now. That is it. So here is homework assignment number 4. You're not doing part C on 77, but you are doing the rest of these, and we will go over these in class tomorrow. Also, guys, just so you know, tomorrow we're going to do some extra practice with this from some old AP questions. And on Monday, you're going to have a quiz on the logistic model, okay? You're going to do AP practice tomorrow, and on Monday you're going to have a quiz. Then we have one more topic to learn. We're going to learn about arc length, and then your test is going to be next Thursday, or at least that's the plan as I'm making this video. This may have changed. I'm making this way in the past. But the test as of right now is next Thursday, which is October 10th. Okay, so the sub will correct me if I'm wrong with this, but as of right now, the test is scheduled for next Thursday, October 10th.